everyone, this is Varun. Welcome to Aerospace Structures. Today we are going to discuss about the application of energy method. In previous classes, we have discussed about the energy method, that is the strain energy and complementary energy. Now we are going to discuss their application. Okay, now the topic is the principle of stationary values of a complementary energy. And here you need to know what is meant by a stationary value. For example, let us take a graph like this and function f of x on y axis and x. And what you observe in this graph, you have observed that minima and maximas. At a point of either minima or maxima, we have f dash equal to 0. F dash of x at a point equal to 0. And here also it is f dash of x equal to 0. That is, the function is neither increasing or decreasing at that point. Either it is at a local maxima or local minima. And the point is called as a stationary point. And similarly, when we have a complementary function for a given loaded system, let us look whether it has a complementary it has a stationary value or not. And this is the concept of stationary value for a function f of x. This is a mathematical representation. Okay, let us take an arbitrary body. And it is hinged at one point and another point. Now, if we apply a load P, it produces a deflection of some magnitude delta. If we release this load, that is P, and we apply a load of delta P, then this delta P produces a deflection of delta x, and previously let us consider it as x deflection is, and for delta P the deflection is delta x. Now if we apply the same load of magnitude P, then the deflection will be x plus delta. And here what you have observed, first case, when you apply a load P, you have obtained a deflection of some magnitude x. For time being, don't consider the x as something variable. It's just a mere representation of deflection at certain point. And if I apply a load of delta P, after removing this load, it has produced a deflection of some delta x. And if I produce a load of P plus delta P combinedly, then the deflection will be x plus delta x. This is not equal to, here what you have observed, that is there is some relation between this load and deflection, and we say that it follows the principle of superposition. Okay, let P1, let us take an arbitrary body once again. This is an arbitrary rigid body. That is, there is no rigid body, means there is no translations, only deflections. Let us apply a load of magnitude P1, P2 in some random load and some load of Pn. As a result of this, what we have obtained is that the deflections like delta 1, delta 2 and so on, delta of n. And if we apply a visual force of delta P1, delta P2, so on, delta Pn, let us see what happens for an elastic system. This is the case for a linear elastic system, only valid for a linear elastic system. Okay, now the total virtual work done by a elastic system is given as minus integral, that is along the volume, into y dp plus integral r equal to 1 to n delta r and delta p. Sorry, this is delta pr. This is the mathematical statement for the virtual work done on a system. For example, when you take a truss structure like this, which is fixed at one point, and we have applied a load of some magnitude P1, some P2, and some here it is P2, and we have observed the deflections of some say delta 1 and delta r. Here integral minus integral y dp is acting on an elastic system, that is it is an internal work done or the elastic work done. It is something like a complementary energy which is integrated over the volume of a system. And the second thing, this has been appeared because of the applied load. When a load is applied on a system, we have found that there is a virtual displacements on a system, and this virtual displacement produce a work done, the virtual work done, and we are representing that virtual work done by the following, that is the deflection magnitudes the load gives the virtual work done. Finally, what we can represent here is that delta Ci plus Ce equal to 0, that is the total complementary energy of a system is equal to 0. Here the delta is a small variation, and Ci because of internal forces which is given by this equation, that is minus integral volume y dp, and Ce because of external load which is given by sigma r equal to 1 to n delta r and pr. Here you might have identified what this r is. For example, if we have drawn a truss like this, okay, this is a truss, or simply saying it is something like a structural element. If we apply a load P, there is a magnitude of deflection of delta R. It represents this the number of loads applied on a truss. And finally, what we can say is that for an elastic body in equilibrium under the action of applied forces, the true internal forces or stresses and reactions are those for which the total complementary energy has a stationary value. In other words, what I can state is that the external loads applied on a system is balanced by the internal force existing within the bodies. Next, this is a typical truss element. Let us apply the principle of virtual work or the application of energy method to this system. You might have observed it is a roller. There is a roller at point B, and it is hinged at a point A, and we have applied a loads of magnitude P1, P3, Pn, and P2, and this is a point C where we need to and our main aim is to find the deflection at a point 2, that is deflection delta 2 at a of a load P2. When we apply a n number of loads, we need to identify for a specific load how much deflection has been occurred for a given system, and the system geometry was given as follows. Let us go through this. Okay, the first thing what we need to do is that we need to construct a total complementary energy of a system, and you might have known this. For example, when you have a rod which is fixed at one end, it has a material property of E and a geometric property of area and length L. The deflection produced by this rod when we apply a load P is given as delta is equal to PL by AE. I request students to remember this formula. We'll be using this in our next coming lectures. Similarly, when you observe this truss, we have applied a loads of P1 to N, and these loads have produced a deflection, that is the axial deflections of delta 1 to delta N, and further the total complementary energy, which can be written as C equal to sigma I running from 1 to K integral 0 to Fi lambda I dFi minus into sigma R equal to 1 to N delta R and PR. And here you might have observed that this R is running from 0 to N, that is the number of loads applied. And moreover, you might have seen that I is equal to 1 to K. K is the number of elements within the structures. One should not be confused with these notations of sigma. One is we need to identify how many elements are present in a given structure, and we need to also identify how many loads are applied on a given structure. And finally, lambda I is the extension of the ith member. The ith member might be somewhere in between this stress delta I, and Fi is the force in the ith member. This is the force acting Fi. And remember, here the force is due to the applied load. Applied load is completely different from the force which we are discussing. When we apply a load, there is some force which is acting within the member. That might be a compression or tension. And next thing, R corresponding to displacement of the rth load P. This is the statement of our problem. Now we have complementary energy, and we have identified the number of elements in a truss, and we have a extension of the member. Let us proceed. From the principle of stationary value of total complementary energy. Now we apply the principle of stationary value of a complementary energy. And what it says is that when you differentiate this with respect to some magnitude of load, what we get is we have a complementary function which is running from I equal to 1 to K. This is lambda I dFi and minus sigma something like R equal to 1 to N delta R and PR. Now if we expand this, for example, if we have a 3 members, if we have applied only for 3 loads, what we can write is that, and here we have only 2 elements, just like let us consider a structure like this, and we have applied a load. This is a mere representation, and that what we can write is that for this C equal to sigma I equal to number of members 1 to 2. What we can write is lambda 1 dF1 plus lambda 2 dF2, and we have 3 loads, let us say P1, P2 and P3. As a result, we have 3 deflections. What we can write is delta 1 P1 minus delta 2 P2 minus delta 3 P3. Now, if we differentiate this C with respect to some load P, let us say load P1, dou C by dou P1. And what we get is that lambda 1 dou f1 by dou p1 plus lambda 2 dou f2 by dou p2. And finally, in this, what we get is minus delta 1. All the things has been vanished here. And similarly, the same case, when you have some equation like this, and when you differentiate it with some specific value of load, say either by P1 or P2. Now, for our case, let us take for P2. If we differentiate this equation with respect to P2 and what the other loads from P except P2, the other loads vanishes, and differentiation of P2 with respect to P2 gives 1. Finally, what we get is this equation. Now, what we know is that we already know the force existing in a member. We can calculate through the method of joints whatever might be. If we know the F1, and we can also determine dou Fy by dou P2. And what we need to determine is that this is lambda I. Lambda I is not an eigenvalue. Don't be confused with the eigenvalue. It is an extension. It is given as FIAI divided by EILI. Okay, thank you very much. This is Varun Moruganti signing off.
Like, share and subscribe. Hit the bell icon for more updates.